Next is a case study by the Gold Coast Rapid Transport Route. This is following on from some of the comments by Mike Jensen, and have Dylan Coote and Hinson Wu from Arup, I've left off the S this time, who actually will go and discuss this case study of working on this job and how their team approached it.
Afternoon, everyone. Today we're here to essentially give you a brief overview of the Gold Coast Rapid Transit project, how Arup was involved in the project, how we effectively used 12D and had a very robust system for the project. And Hinson will also discuss how Arup and 12D collaborated on a certain suite of rail-specific tools that definitely assisted us in moving forward with the design. First, a bit about ourselves. My name's Dylan Coote. I'm a civil designer with Arup. I've been on the project for about 2.5 years since the tender phase. Over that time, I've done a lot of the alignment design, design coordination. Currently, I'm out on site handling site queries and doing the designer certification.
Hi, ladies and gentlemen. My name is Hinson Wu. Just give you a bit of background myself. Yeah, I had highways design background, and I've been working on a number of rail projects back in the UK, ranging from network rail to the high-speed 2 rail projects, which people might heard about, from the London all the way going up through Birmingham to Leeds. Recently been transferred over to the Brisbane office for some new challenge. I've been working on some local projects, and certainly GCRT, Gold Coast Rapid Transit, is one of the projects I've been enjoying and working on. So not wasting any more time, I'll pass it back to Dylan to carry on with the presentation. Cheers.
Yep, so I guess we'll just start off with a bit of an animation. The section of the project we're working on is the first part of 3 stages. It's 13 kilometres long. It links the Gold Coast University Hospital, essentially where that little blue dot is down in the left-hand corner of the screen, and runs through Southport, Surfers Paradise Boulevard, Florida Gardens, and eventually terminates at Broadbeach. The project has been funded by the federal government, the state government, and has been a significant contribution by Gold Coast City Council. I believe it's to the tune of about $1 billion or close to. At the start of the project, at the start of the alignment, we call it the northern end of the alignment, there's a tunnel portal that contains a station between Gold Coast University Hospital and Griffith University. It's 250 metres long and sits underneath the road. As the rail, oh, there we go, there's a picture of it during construction. Okay. As the rail daylights from this tunnel, it goes up Parklands Drive to Griffith University Station. Griffith University Station is one of the 4 LRV stations that has a bus interchange connectivity type thing. Okay. After Griffith Uni Station, the rail alignment lifts up onto a 400-metre viaduct. This viaduct spans the Smith Street motorway and also spans a fairly significant environmental section of the Gold Coast. From here, the viaduct lands on a piled track slab and access to the LRV depot. Hinton will give you a bit more about that.
As you can see, this is a footprint of the depot. The depot have those standard features like chain washing plant, sand washing plant, depot office building, and also we have 7 sidings in the depots with 2 additional siding for future capacity if there's a need. There's another picture of the depot. The depot is actually built right next to, very close to an old landfill site, and the depot itself is having built on a track slab rather than normal ballast track, and supported with approximately about 300 number of piles, and per pile is probably about 20 meters depth. This design is actually a very this design is actually quite different to the tender phase. It's a very optimized design with an innovative approach. Tremendously reduce the footprint size of the depot. The whole depot is probably about 220 meters length times 120 meters width. So it's quite a small one, but without compromising on the functionality of the depot.
Right. Yeah, as Hinston touched on, the whole depot is actually founded on piles. The reason for this is the area is an old landfill site. The geographical location of the depot itself sits in amongst an industrial area and also next to the Gold Coast City Council depot. So I guess it's a fairly good sustainable use of the land. I really don't think they could put much on there apart from a dirty old rail yard. All right. Queen Street Station. This station essentially services the industrial area just to the west of it and the residential area just to the east. The alignment goes up Queen Street and then turns up Nerang Street. Nerang Street Station sits outside the Gold Coast Hospital and the health precinct around there. I guess while we're here, it's worth noting that the civil works between Queen Street Station and just north of Nerang Street Station were done as part of an early works contract. So essentially during our tender phase, I think it was Seymour White, we were out there building, widening the road and essentially leaving a nice rail corridor for us to come and build in. Okay, so we go up to Southport Station. Southport Station sits up the end of Nerang Street. Nerang Street's actually going to be closed off from the station and the whole area will be pedestrianised, there'll be more, there'll be some good landscaping features. This is another one of the interchange areas where essentially you alight from the LRV and there's bus stops fairly close by. All right, Scarborough Street, if any of you know where Australia Fair is, it sits right on the edge of Scarborough Street. On the opposite side there's another shopping centre. It's a fairly constrained location. This was a fairly testing area and the interfaces between the rail and the civil guys really came into play there. We'll talk about that in a minute, how 12D assisted us with that. Okay. We have the LRV crossing the Nerang River. It sits next to the existing Nerang River Bridge. For aesthetic purposes, we've kept the alignment the same as the Nerang River, the Nerang River Vehicle Bridge, and also for maritime and flow purposes, we've kept the piers in the same alignment. What's not shown on this photo, on the other side there's a pedestrian bridge. That pedestrian bridge obviously links either side of the river, but it'll also link a new shared pedestrian path all the way down into Surfers Paradise. Right. Through here, the rail operates at about 70 k's. That sits outside the Gold Coast Highway. Oh, it's a bit of a gimmicky V8 picture. Why we've got this up here is because this corner in particular, so the corner of Gold Coast Highway, Fernie Avenue and Surfers Paradise Boulevard is one of the bends for the V8 circuit. With this interface, it left us with next to no space to put essentially a rail down the edge in between the buildings and whatnot. So during the event, the V8 track, the marshalling area and the grandstands will actually utilise part of the corridor and the rails will just operate on a single line. So both the southbound and the northbound services will operate on the same line with crossovers at either end. All right. We come down Surfers Paradise Boulevard. Sure, a lot of you know that this is one of the higher touristy areas of the Gold Coast. We have 5 stations in very close proximity. That's sort of replicating the amount of use that should be put into this area. One thing to note at the moment, Surfers Paradise Boulevard is generally a 2-lane, 2-way road, and a lot of vehicles use this road to rat run through the Surfers Paradise. When the LRV goes in, that'll be reduced to a single lane southbound road. Hopefully this will promote the use of that road as simply a local access for deliveries or people getting back to their hotels. With this arrangement, we feel that there'll be a lot more focus on pedestrians throughout the area and public transport. So fingers crossed it'll lift the amenity of that whole area up for the general users. Yep, so now we're back onto the Gold Coast Highway. Through here, this is another section where the early works were taking place early on to essentially create the rail corridor. We've got a station outside the convention centre, and the end of this line is Broadbeach South Station outside Pacific Fair. I guess this is a fairly unique station because you can alight from the LRV either side onto either platform and get straight onto a bus. So the platform actually shares the same platform as the bus. Yeah, just some quick system facts. There'll be 14 LRV vehicles for this stage of works. Each vehicle is 43 metres long. The top operational speed is 70 kilometres an hour. Each vehicle has a capacity of 309 passengers. There's 16 stations. It's approximately 37 minutes end to end, and it will work on the TransLink go-card ticketing system. All right. The project's been delivered via a PPP, public-private partnership. The consortium that is undertaking that is GoldLink. It's made up of an operational and maintenance arm and the design and construct arm. The operational and maintenance arm is KDR, or Keolis Downer Rail. It's a joint venture. And the design and construction arm is McConnell Dow and Bombardier. McConnell Dow are delivering the civil aspects of the project, the rail alignment, everything sort of under the rail alignment. Bombardier are delivering the rolling stock, the rail systems, and also the OHL. In terms of what Arup has contributed to the project, we've been the consultant or the engineering consultant to McDowell since the tender phase. Primarily it's rail, civil and structures. Some other disciplines are geotech, noise and vibration, flooding and the like. Okay, this is a 3D version of a typical section. It hasn't been taken anywhere in particular, but it sort of demonstrates the interaction between all the different design elements for the LRV sitting in a constrained corridor. If you have a look down the middle, you obviously got your LRV. You know, what we've modelled in 12D, we modelled the system conduit sitting underneath that for space proofing purposes, the alignment, the track obviously. The rail guys actually modelled the vehicle envelope or the swept path envelope and the clearances. I personally think this was the single most beneficial tool that we had in that interface. Outside this, you got all your standard civil items, so your road alignment, pavements, verges, curbs, drainage, etc. All right. During the tender stage, we used a combination of MX and InRail to design the works. This was primarily done because a lot of the designers were very used to these two tools. What we found as we started the design, we had a lot of issues with information sharing between the two software packages. When we had a very high level or a high program of design, a lot of the time exporting and importing the data was just left off, and some people were working with old data and whatnot. Also, the obvious risk that the obvious inefficiencies that bring was an issue. So during the detailed design, the decision was made that, okay, we'll use 12D for all the civil, rail and drainage works. This obviously allowed us to streamline sharing of the projects and sharing of our models. It also meant that we could collaborate quite easily with all the other parties using the 12D platforms such as McDowell, who are doing all the survey, or Cardno, who are doing a lot of the services coordination and design. Just while we're here, we also used AutoCAD for a lot of the drawing production, and ProjectWise was used for the file management. I guess when we did decide to use 12D on the detailed design of this project, we had a few issues or teething problems that we identified. One of these was the rail capabilities in 12D at that time were quite lacking, and Hinson will go through how 12D collaborated with us to get a really good result for the project. Also, there was a number of designers or 12D users on the project. I think at the peak we had approximately 25 with a core team of about 13. And we needed to create a very simple, easy to use, robust 12D project setup to manage the models, but also make sure everyone was on the same page. Okay, so in terms of the 12D project, this is how it was broken down. We have obviously the Gold Coast Rapid Transit project. The Pacific zones in that project were broken down by Arup at the start, and these have now been adopted across the whole project, specifically for the chunks of design for one person to do. So under each zone, we've got a road project, a rail project, a drainage project. Then some other parties did the PUP, and McDowell did the the survey DTM. Under each one of these projects, we had the minimal amount of models that we had to have. So we've essentially split it between alignment models, which was the base data for the project, so all your alignment strings, and then just a single design model for each project. So this was only the design strings or something that represented the physical form once built. Right, it's just a bit of a spreadsheet that we use to manage that process. As you can see here, we've got the 5 or 6 alignment models. The design strings that we used from those alignment models were fed only into those 2 design models. So if you took those 2 design models, you'd have all the physical information for what will be built at the end of the day. Okay, model management. Yeah, this is just to try and reinforce that message that it was a large project. It was a 13-kilometre rail and road project. Split into 6 zones. We had 60 signalised intersections, and from the 12D perspective, we had about 600 apply functions. From this, we've managed to squeeze those elements into 6 civil design models, 6 rail design models, and 6 drainage models. So it was really compressed and easy to manage. Road rail interface. This is just a bit of a section indicating where our responsibilities lied as a rail designer or a civil designer. The pink demonstrates the rail corridor. However, outside of that rail corridor, you have the modelling of the vehicle swept path and the clearance zone. So like I said before, that was very beneficial to try and squeeze everything up but not go too far into sort of a hazard zone. All right, I'll pass you over to Hinson.
So I touch on a little bit on the key issues for the light rail design. Besides the standard permanent way issues like the design turnout, crossovers, and the overhead system, signal system, etc., etc., the important bit is the geometry issues on the rail calculations bit. Certainly, CAN application is one of the important bit. Thanks. And CAN application is CAN is actually described as the vertical difference between low rail and high rail, and is almost quite similar to the superelevation that people use for highway design. SSD stands for side stopping distance application, which is quite essential as GCRT project is actually sharing the corridor with other road users. DKE developed kinetic envelope and clearance, which Dylan just mentioned about in the previous slides. That's definitely very useful when we have 12D working together with everyone in terms of the civil coordination and everything. Allow me to move on to the macro development on the railcan macro. This is a unique challenge to the design team for using 12D. CAN is applied and described, like I mentioned before. The rail alignment is designed at the rail control line with CAN macro applied by adjusting the high rail accordingly to suit. So it's actually different to any highway projects that don't have any low rail, high rail on a highways project. And besides all these problems that I just mentioned before early on the key issues on the light rail design, to tackle all these problems before having these macros is quite a challenge to the design team, and we are so delighted to have the 12D developer working so closely with us with the fast turnaround, working together with us with the very tight time schedule. So we really want to, before I move on, I really want to express our thanks to the 12D developer and Mike Jensen, definitely, if you are here just now, early on with the previous speaker. Much appreciated, and thank you to the 12D developer. So I'll move on to this again. Another screenshot on the railcan macro. It allows us to input any design limits in the macros. Summary table shows the calculations and a simple graph. This is important. These output panels to string modifiers. It actually allows us to output the information into respective string for the rail. And let me show you a screenshot of the actual 12D application. Once we have all this information input correctly, it's almost an automatic process. The output, it allows us to output the modifier panel of the MTF to apply cant onto a number of strings. It's a number of strings, not just one. And in order to do that manually, it's going to take us long time to do that. So with this macro development, it really speeds up the process tremendously. And it also allows us to, especially for GCRT, Gold Coast Rapid Transit, this project, the rail is actually embedded into a concrete track slab and connected to the roads, curbs, footpath, drainage feature, etc., etc. So these CAN macros really enable the close coordination with the road designer, track form designer, drainage designer to ensure an accurate and detailed cross-section produced at the end of the day. Of course, the advantage of the CAN macros, which I mentioned before, is really save us a lot of time and reduce a lot of human error, but provided we have input everything correctly in the beginning. Quickly move on to the stopping sight distance macro. I'm not going to, bore you guys about stopping sight distance. This is a fundamental and very essential checking process that any highway designer have to go through. And it is a repetitive engineering process, very time consuming as well. After you're doing a few rounds of the stopping sight distance check, I must confess it's quite boring, but it's essential purely for safety purpose. I'm going to move on to show you a little bit on the development of the stopping sight distance macro. It is a really dynamic approach. It's very different to the standard sight stopping distance that already built in the normal traditional 12D. We actually get the information like the deceleration tables from the operator, which is Bombardier, for this instance, to actually get the specific characteristic of that particular rolling stock for this project input into the macro, because this deceleration is going to change based on different speed, different gradient. And the beauty of the macro is they can actually input a number of different characteristics of the rolling stock at the same time. For example, the surface braking and emergency braking at the same time. Let me show you a bit of the, this is the screenshot of the macro itself. The green line in the graph indicating the achieved sight stopping distance. The orange and the red line indicating the required sight stopping distance based on different braking rates. Anytime you see a green line conflict with the orange or red line, it indicating that there is a problem. So we have to go back to the design, redo the alignment, or remove the obstacle if you can. And at the end of the day, what we want to achieve is the green lines is above all the green line, which is the achieved sight stopping distance, meeting the minimum requirement. And as I mentioned early on, we have if you look at the green box on the top, we have a few different options to go in to calculate the tables. It's not just using the deceleration table. We can use the distance table. We can also use a constant rate if it needs to be. Like any highway design, we have a coefficient to put in constantly. But it allows the flexibility in this macro that you can apply different characteristic of the rolling stock into the macro. So after the GCRT, when we come to another rail project, we can simply get the another set of data, and then put it into macro, and then off you go. This is another, just showing you, the graph can be a little bit complicated. This 12D macro can also output our results in Excel format very easily, and it also allows you to look at where it fails and where it passes, quite easily identified based on the drainage on the alignment. So, after all, it all sounds easy and simple. It's just a press button process. But actually, I must confess I'm lying. It takes us a lot of hard work in the beginning. We have to model the rail corridor and plus the road corridor very carefully. The green color bit is actually the survey model that we created. And we also have to create any obstacle, which is showing in the gray color bit. Is the any building boundaries, obstacle, fencing, bridge piers, retaining structure, anything, even heavy vegetation. So we have to build everything into a super tin very carefully and accurately in order to get a better result at the end of the day for the side stopping decent check. You can also see if people have a sharp eye, you can also see the left-hand side, there's the depot there. Another, just a screenshot to show you a bit close up. Besides modeling just the side stopping distance, this macro also allows us to check the signal sighting along the route. This is actually quite useful for the signal designer. As Dylan already mentioned, we have nearly 60 number of intersections and with at least 2 sets of traffic signals along each intersection. So we have to make sure that the tram driver actually can see the signals in order to stop. I've just mentioned the 2 macros that we've been developed together with the 12D developer, and the macro itself is not just an innovative approach, but it's also quite sustainable because it can be used on any other projects as well. So when I come to the rule of thumb for the design, very quickly, this is actually the most important slide. When we put in $1, we get $1. If you put in rubbish, we get rubbish as well. So the more money you put in, or the more hard work you put in the beginning, we got more. So the actual summary is you get what you actually put in. So that's the end of our presentation. Thank you very much.
I must make the comment, we don't care what software you start with, as long as you end with 12D model.